Jack Kilby didn't look like someone who would ignite a revolution. At 34, he was a quiet engineer with thick glasses who specialized in tiny components for hearing aids. But in the summer of 1958, while his colleagues were on vacation, Kilby solved a problem that was strangling the electronics industry. And just like that, the world began to shrink. The problem wasn't creativity or ambition, it was mathematics. As circuits grew more complex, the number of connections rose dramatically. A simple amplifier might need dozens of solder joints. A computer required tens of thousands, and eventually far more. Each connection represented a potential failure point, and failure rates were climbing faster than performance gains. But the connections themselves were becoming the enemy of performance. Long wires between components created signal delays that slowed circuit operation. Parasitic capacitance between closely spaced conductors caused unwanted electrical coupling. High-frequency signals suffered interference and distortion as they traveled through increasingly complex wiring networks. The very architecture that enabled sophisticated circuits was simultaneously limiting their capabilities. Miniaturization made these problems worse, not better. Smaller components required finer wires and more precise assembly. Technicians working under microscopes struggled to make reliable connections between parts that were approaching the limits of manual dexterity. Quality control became dramatically more difficult as circuit density increased. Industry leaders called it the tyranny of numbers. The phrase captured a brutal reality. Electronics were becoming too complex to manufacture reliably. The U.S. military, pushing for smaller and more powerful equipment, was particularly frustrated. Their missile guidance systems needed circuits that were simultaneously more sophisticated and more reliable than anything commercially available. The scale was staggering. A single advanced computer of the era could require over 500,000 hand-soldered connections. With that many points of failure, the laws of probability dictated that the machine would almost never function perfectly for more than a few hours at a time. Manufacturing costs were spiraling upward alongside these physical constraints. Complex circuits generated enormous amounts of heat, requiring cooling systems that added weight and bulk. The most advanced computers filled entire rooms, yet performed calculations that today's pocket calculators handle effortlessly. Kilby had joined Texas Instruments in Dallas earlier that year. TI was expanding rapidly, driven by military contracts and pressure to innovate in the competitive semiconductor market. The company culture emphasized ambitious projects, even when the path forward wasn't entirely clear. But Kilby's timing created an unexpected opportunity. 2 weeks after he started, TI shut down for its annual summer vacation. Most employees took 2 weeks off, leaving the facilities nearly empty. As the newest hire, Kilby hadn't accrued vacation time. He would spend the shutdown period alone in the lab. The empty building gave Kilby something rare in the electronics industry: uninterrupted thinking time. Without meetings, phone calls, or collaborative projects, he could focus entirely on the fundamental problems facing circuit design. The isolation was complete. The usual bustle of engineers debating approaches and sharing insights was replaced by silence. There were no senior colleagues to consult and no established protocols to follow. Kilby had only his notebook, boxes of semiconductor samples, and access to fabrication equipment that few people fully understood. This solitude forced a different kind of problem solving. Instead of incremental improvements to existing approaches, Kilby could question the fundamental assumptions that guided the entire industry. The absence of collaborative pressure allowed him to pursue ideas that might have been dismissed in group settings as too radical or impractical. He began by examining the basic assumptions underlying electronic manufacturing. Every circuit started with a substrate, usually a piece of plastic or ceramic, onto which individual components were mounted and connected. The components themselves were manufactured separately: resistors in one factory, capacitors in another, transistors in a third. This approach made sense from a manufacturing perspective. Specialized factories could optimize their processes for specific components. But it created the connection problem that was strangling the industry. Kilby started sketching alternative approaches. What if, instead of assembling separate components, all the parts could be created from a single piece of material? The idea wasn't entirely new. Researchers had discussed molecular electronics and integrated circuits in academic papers. But no one had built a working prototype. The key insight came from understanding semiconductor physics. Transistors were made from silicon or germanium, materials whose electrical properties could be precisely altered through a process called doping, or adding tiny amounts of other elements. Kilby realized these same materials could be chemically treated to act as resistors and capacitors, effectively turning a single slice of crystal into a multifunctional machine. Kilby realized that a single piece of semiconductor material, in his case the germanium that Texas Instruments was already mass-producing, could contain all the components needed for a complete circuit. Instead of mounting separate parts and wiring them together, the entire circuit could be fabricated as one integrated unit. He filled notebook pages with calculations and sketches. The concept was elegant. Start with a small wafer of semiconductor material, then use chemical processes to create different regions with different electrical properties. While he eventually envisioned metal traces deposited on the surface to provide connections, for his first physical attempt, he would have to rely on delicate, hand-soldered gold wires to bridge the components. The approach would eliminate thousands of hand-soldered joints. It would also make circuits smaller, lighter, and more reliable. Manufacturing could be automated, reducing costs and improving quality control. In July 1958, Kilby wrote in his lab notebook that circuit elements including resistors, capacitors, and transistors could be made on a single slice of germanium. He sketched a simple oscillator circuit that could demonstrate the concept. Building the prototype required improvisation. TI's fabrication equipment was designed for individual transistors, not integrated circuits. Kilby had to modify existing processes and invent new techniques. He started with a piece of germanium about half an inch long and thinner than a paperclip. Using chemical etching and hand-attached gold wires to connect the elements, he created the circuit. The process was crude compared to later manufacturing techniques, but it could demonstrate the fundamental concept. The first attempts failed catastrophically. Chemical etchants ate through protective layers, destroying entire circuits. Temperature variations during processing caused the semiconductor material to crack. The delicate gold wire connections frequently broke during handling. Kilby spent days troubleshooting each step. The chemical etching had to be stopped at exactly the right moment to avoid over-etching the delicate circuit features. The wire bonding required steady hands and precise positioning under a microscope. Contamination was a constant enemy. A single speck of dust could ruin an entire circuit. The lab's air filtration system wasn't designed for the precision work Kilby was attempting. He improvised clean room techniques, working under makeshift hoods and using filtered air supplies. The yields were abysmal. Most circuits failed outright. The remaining circuits often had defects that made them unreliable or non-functional. Each failure meant starting over with new materials and modified processes. Management grew concerned about the costs. Military contracts had specific deadlines, and resources were being diverted to Kilby's experimental project with no guarantee of success. Senior engineers questioned whether the integrated approach was fundamentally sound or simply multiplying failure modes. The pressure to abandon the project intensified as weeks passed without tangible results. TI had profitable transistor production lines that required engineering attention. Some managers questioned whether the company should continue funding what appeared to be an expensive academic exercise with no clear path to commercialization. The connections between components proved particularly troublesome. Traditional circuits used thick copper wires that could carry substantial currents. Kilby's gold wire connections were microscopic by comparison and frequently broke during processing or testing. Even when the circuits survived fabrication, they often failed during operation. The thermal expansion of different materials caused stress fractures. Electrical interference between closely spaced components created unexpected behavior. The circuits were far more sensitive to environmental conditions than discrete components. Kilby methodically addressed each problem. He experimented with different materials, modified processing temperatures, and developed new techniques for creating reliable connections. The work required both theoretical understanding and practical craftsmanship. After weeks of failures, Kilby achieved his first stable circuit in late August 1958. The components functioned correctly, and the connections remained intact during testing. but the circuit was still too fragile for practical use. He spent additional weeks improving the robustness of the design. The final prototype used more stable materials and improved connection techniques. The circuit was crude by later standards, but it was reliable enough to demonstrate the concept. On September 12, 1958, it worked. The lab was empty. Kilby connected an oscilloscope and watched a clean sine wave appear on the screen, the signal holding steady. A complete electronic circuit could exist on a single piece of semiconductor material. The architecture of electronics had changed. TI's management moved quickly to file patents and explore commercialization, but Kilby's invention faced skepticism from the broader industry. Many engineers doubted that integrated circuits could be manufactured reliably or economically. The skepticism wasn't entirely unfounded. Initially, these circuits were expensive and limited in complexity. They couldn't match the performance of carefully hand-built circuits, leading many to believe they would remain a niche technology. Meanwhile, 1,500 miles away, another engineer was pursuing the same breakthrough. Robert Noyce at Fairchild Semiconductor had independently conceived of integrated circuits. His approach used silicon instead of germanium and employed a different manufacturing process. Noyce had arrived at the concept through a different path. While Kilby focused on eliminating connections, Noyce was trying to solve the problem of isolating components on a single substrate. His solution was more elegant, a planar process that created natural barriers between circuit elements. Noyce's breakthrough was the planar process. By using silicon and a flat layer of aluminum to interconnect the parts, he eliminated the need for Kilby's delicate, flying wires. This made the integrated circuit truly flat, durable, and, most importantly, ready for mass production. It was the blueprint for every chip that would follow. The parallel development created a patent war that would consume both companies for several years. The legal dispute began in 1961 when both TI and Fairchild filed competing patent claims. Each company argued that its engineer had conceived the integrated circuit first. The stakes were enormous. Integrated circuits represented a market that many believed would eventually be worth billions of dollars. Whichever company controlled the basic patents would dominate the emerging industry. Both TI and Fairchild invested millions in legal fees, hiring teams of patent attorneys and technical experts. The dispute created uncertainty throughout the electronics industry, with potential customers delaying adoption until the ownership question was resolved. Companies wanting to use integrated circuits faced the risk of patent infringement lawsuits. Others negotiated licensing agreements with both companies to avoid legal complications. The legal battle dragged on for years as courts struggled to determine priority. Kilby's germanium-based approach was earlier, but Noyce's silicon process was more practical for manufacturing. In 1966, the dispute was settled through cross-licensing agreements that allowed both companies to continue manufacturing and selling integrated circuits without further legal obstruction. The resolution came too late to prevent years of delayed progress, but it cleared the way for rapid industry growth. Despite the patent complications, both TI and Fairchild pushed forward with development. The military provided crucial early funding, ordering integrated circuits for missile guidance systems and satellite electronics. These applications could justify the high initial costs and tolerate the limited complexity of early chips. The military's requirements were particularly demanding. Missile guidance systems needed circuits that could operate reliably in extreme temperatures, high acceleration, and harsh operating conditions. Traditional discrete circuits often failed under these conditions, making integrated circuits attractive despite their higher cost. Weight reduction was critical for military applications. Every pound saved in guidance electronics meant additional payload capacity or extended range. Integrated circuits offered dramatic weight savings compared to equivalent discrete circuits. Guidance systems could be significantly reduced in size using integrated circuits. Reliability requirements were equally stringent. Military systems had to operate for years without maintenance in extreme conditions. A single component failure could doom an entire mission. Fewer connections in integrated circuits meant fewer potential failure points. This reliability advantage justified the higher initial costs for critical defense applications. The Cold War context made these advantages strategically important. The Soviet Union was advancing rapidly in missile technology, and American military leaders recognized that superior electronics could provide a strategic advantage. Integrated circuits promised guidance systems that were smaller, more capable, and more reliable. Early satellite applications pushed integrated circuit technology in different directions. Space-based electronics needed to be extremely lightweight and power efficient. The reduced size and weight of integrated circuits provided significant advantages for satellite designers working within strict payload constraints. The Minuteman missile program became one of the largest early customers for integrated circuits. Each missile required large numbers of integrated circuits and electronic modules for guidance, control, and telemetry systems. The program's volume requirements helped drive down manufacturing costs and improve reliability. Military specifications were far more stringent than commercial requirements. Circuits had to operate reliably for years without maintenance. This drove improvements in materials, processing techniques, and quality control that benefited the entire industry. The first commercial integrated circuits appeared in 1961. They contained only a few transistors and cost over $100 each, several times that amount in today's dollars, but they offered significant advantages in size, weight, and reliability. Military contractors began specifying integrated circuits for critical applications. As production volumes increased, costs dropped rapidly. By 1965, integrated circuits were competitive with discrete components for many applications. The industry began a period of explosive growth that would continue for decades. Early integrated circuits were used primarily in specialized military and aerospace applications, as most of the industry remained skeptical of their commercial potential. To prove them wrong, Jack Kilby led a team at Texas Instruments to create the world's first handheld electronic calculator. Codenamed Caltech, it was a brilliant PR move that showed the public how integrated circuits could shrink a desk-sized machine into the palm of your hand. But engineers at companies like Intel, founded by Noyce and Gordon Moore in 1968, saw the potential for much more complex circuits. They began developing integrated circuits with hundreds, then thousands of transistors on a single chip. Moore observed that the number of transistors on a chip was doubling approximately every 2 years, a trend that became known as Moore's Law. This exponential improvement in circuit complexity enabled entirely new categories of electronic devices. This exponential scaling represented a fundamental shift in how electronic complexity could grow. Before integrated circuits, more sophisticated systems required more components, more connections, and more space. Each additional function meant additional assembly work and additional failure points. The relationship between capability and complexity was essentially linear. Integrated circuits broke this relationship. More sophisticated systems could be created by shrinking the geometry of existing designs rather than adding more discrete parts. The same manufacturing processes that created simple circuits could create complex ones by making the features smaller. Complexity could grow exponentially while size remained constant or even decreased. The first microprocessors appeared in 1971. These were complete computer processors fabricated on single chips. They were initially used in calculators and simple control systems, but their capabilities improved rapidly. Once entire processors could fit on a single chip, computing no longer required a room. By the mid-1970s, microprocessors were powerful enough to serve as the foundation for personal computers. Companies like Apple, Commodore, and Tandy built entire computers around single-chip processors that cost less than $100. Modern smartphones contain billions of transistors fabricated using techniques that evolved directly from Kilby's original concept. The same principles now operate inside devices that connect instantly to global networks at speeds that would have seemed impossible in 1958. The distance between continents has collapsed into milliseconds, and it all began with one working circuit on a strip of germanium.